Yes, we will wait for Bernard to.
Let us wait. Let us wait.
Okay, friends, I think we are live now, and we are a little bit late this morning on the scheduled time that was 9:15. I believe we will start our panel at 9:30. We had some delay in some train this morning, and okay, some problems. Okay, so I beg your pardon by now and wait for some more 10 minutes to start our panel. Okay, thank you very much. Some problems. Okay, so hello. Yeah, we just started. Okay.
Adriano?
Yes.
Oh, I've been following the conference yesterday via YouTube. I was wondering, because it's quite hard to see, of course, when you're watching like that, how many people were there in the room? How many people were watching present?
Oh, well, there were some tens of people. I think maybe 40 or 50 people, something like that. Yeah.
Very good.
Not so many, but however, yeah.
I think there are some people coming now.
Yeah.
Some people are coming now.
Yeah. Okay, good.
Maybe we'll wait. Yeah, 10 minutes.
We start 9:30. I already said it.
Can't take a coffee, it's time now.
However, we are live already, so people. Hi, John. Hello. Hello, John. Can you hear me? I don't hear you. you talk?
Yeah, can you hear me?
Okay, now I can hear you. Yeah, fine. So we didn't start yet. We are live now, but we didn't start the panel. We will begin in 5 minutes at 9:30.
Okay.
According to the presence of the speakers, the program could have a little variations.
Okay.
So somebody could be called to speak before the scheduled time or later. So we'll see how the people is joining. Okay.
Sure. How have you been, Adriano?
Yeah.
Good.
Yeah. But sorry. Can you repeat?
How have you been?
Oh, okay. You're doing well. It's a big work, of course, making this kind of things.
Yes.
Yeah.
Can you hear me okay? Am I coming through all right?
No, I'm hearing you. Yes, I'm
Okay,
hearing, but yes, I have to still to connect here to the audio of the room. That's my HDMI moment. Okay. Hello.
Up until the last minute, I was really trying to get there. I've never been to Berlin, and airline pilots have been everywhere, but I've never been there, and I've always wanted to go. And but it just wasn't possible. So here I am, virtual again.
Okay, but that's fine. Okay. Yes, we are on the audio of the room now. We were not before. Okay, that's fine. Okay, I will leave you just 2 minutes and be back.
Sure.
It is a blessing, though, that we have virtual meetings and video conference and everything. I mean, it saves us a lot of traveling all around the globe. But for example, John, where are you broadcasting from now?
Are you talking to me?
Yes.
Oh, sorry, I didn't know. You just appeared and you started talking, and I wasn't sure if I was being cut in the middle of the session or what. I'm out in California. It's about it's going on 12:30 here. Yeah, so it's kind of late.
Oh, yeah. I'm in the Netherlands, so quite near to Berlin.
Oh, that's good. Yeah.
Same time zone.
Oh, that's very nice. Yeah, it's going to be a late one for me if I stick around all the way to the round table at the end. Boy, it's going to be probably 3 or 4 in the morning.
Oh gosh.
Yeah, but this is John. No, it's
We are live.
Yeah. So did you record already, or that we are? Do we start to talk? Or?
Yeah, we started, but we are not giving the presentation yet. We will start at 9:30.
Yeah, but you have to do the intro.
You make the
intro. I can do it from here, yes,
It's the same, but then the people will speak here, so it's better to put it here.
But John is the first. He's remote. And the intro is by both of us.
Come on. Okay. Let's make the.
Okay. Oh, okay.
Fine.
Oh, and you have the program. Yes.
Hello. Yeah. Good.
Excellent. So tell me when I can go.
John Mankins is not here. I think Mr. Werner will speak first.
Then John speaks first. Okay, excellent. Okay, so there. Yes, we are starting now. So we are not yet online. Huh? Are we?
We are online.
We are online. So. Excellent, beautiful. So, welcome to the second day of the Space Renaissance International Art and Science Festival that is taking place in Berlin. Ich bin ein Berliner, in the Archenhold Observatory. And so we had a great day yesterday where we are talking about some of the philosophical and also sociological and human aspect of expansion into space. Today we have a dedicated session about habitats in space, on the moon and Mars, and astronauts. And so we have a quite full, intense session that is to come today. Of course, for expansion into space, we are very attached also to look at the technical and other aspect of building habitat in space, designing them, building them, promoting them, and also we will hear also about some analog habitat that we have built on Earth to demonstrate and also to learn how we are going to operate them in space and leading to future settlements. So that's introduction. And so the first talk that we have this morning is by Werner Grandl. And he will talk, you will introduce your talk. So the exact title of the talk is, should have brought my wine glasses, about orbital habitat, and in particular, the O'Neill concept, but also some derivative ideas that he has developed recently with some colleagues. He is also leading a group that we have at Space Renaissance International, a committee that is looking at options for orbital habitat. So, Werner, thanks. Please come on stage. Hello.
Thanks a lot.
Thank you.
So I have a push buttons. Yes, good morning, everybody. I would like to have a little talk about the O'Neill concept of space habitats in the near Earth space, especially between Earth and Moon and at the Lagrangian points of the Earth-Moon system. As many of you know, Professor Gerald K. O'Neill, he passed away in 1992. He was the director of the Space Studies Institute in Princeton, and his crucial thesis has been the best place for humans to live in space are rotating spheres and cylinders made of lunar and asteroid material. By centrifugal forces, artificial gravity, similar to Earth, can be created there. If you think at Moon and Mars, they have much less gravity. So in the opinion of Mr. O'Neill, spheres and cylinders made by humans are the best sites for humans to live in space. The O'Neill colonies should be built, of course, at the Lagrange point of the Earth-Moon system, L4 and L5. This is where there is an equilibrium of the gravitational forces of Earth and the Moon. The raw material for the construction should come from our Moon and from near-Earth asteroids. O'Neill and his students developed the lunar mass driver, where the material from the Moon, which is of course mined in the Moon, should be shot from the lunar surface by how it is called, by a lunar mass driver. It is based on the physics of electromagnetic levitation. You see it in the picture below. Next slide, please. Yes, this is the famous O'Neill Island 1. It is a spherical human colony for about 10,000 inhabitants. If you see it is a sphere, but there are also some toroidal structures which provide agriculture. The mass of the structure and the shielding against meteorites and against cosmic rays would be approximately 3 million tons. You see on the left side a very famous drawing by an artist of the 1970s, and on the right side you see a section where you can see the solar light, or we can say the path of the solar light from outside, from space into the habitat. Next slide, please. Yes, then there were some concepts by Gerald O'Neill. You can see here the so-called Island 3. It is a very utopian concept and should be the maximum design of O'Neill, with 32 kilometers in length and a diameter of approximately 6.5 kilometers. Now, what we can see here is there are such problems which maybe occur if you build such a big structure. First of all, the huge glass areas are exposing the colony to meteorites and of course also to rays and especially to solar flares. And what is also a problem which may occur is you have to adjust every day the great giant mirrors by steel cables, which will cause enormous tensions when you do that. But it is very nice as a concept. Next slide, please. You can follow here. Okay, thanks. So I need my glasses. So a first improvement of this O'Neill concept were made by Antonio Germano, an Italian friend who has unfortunately passed away some years ago, and by myself. It was published within the proceedings of the 11th SSI Princeton Conference in 1993. Now, what were the problems we had to deal with? We wanted maximum safety against cosmic rays, solar flares, and the meteorites. So we had to minimize the window areas on the top of the colony. And so sunlight would have been collected by an array of parabolic mirrors outside the colony and beamed inside along the central axis. You see it on the right side, on the picture on the right side, on the very right side. And then the sunlight would have been distributed by a central cone with mirror facets. Then the second problem is to reduce the mass of the shielding material. We proposed a separate solar flare shielding, which would have been built outside the colony. You see it on the right side. It is entirely covered with solar panels, and the energy would have been beamed to a red antenna near the spaceport of the colony. Next slide, please. Yes, these are some drawings from 1993, very old. We made many considerations about structural stability. There are some external loads, of course, because you need maneuver thrusters for the rotation and for attitude control of such a big structure, of course. And to get a stable spherical or cylindrical design, we thought that a structural framework between an inner hull and an outer hull and outer shell would probably be the best solution. The outer aluminium shell carries the fused rock radiation shielding and the foam glass thermal insulation. The inner aluminium hull would be covered with foamed slag and a routing medium for the landscape. You see it on the right side. You see the inner hull in a section, and of course, it is self-explaining, I think. So next slide, please. Yes, so we tried to move the landscape. Now, structural engineering and climate conditions are limiting the maximum size, of a cylindrical colony to approximately 8.2 kilometers length and 3.2 kilometers in diameter. We have a proof. You can read our paper from 1993. To provide steady rotation of the colony, the land and the water masses should be distributed in symmetrical order, in our opinion. The pictures below show the maximum solar arc for approximately 260,000 inhabitants and a mass of about 350 million tons. If we look at the right picture, at the right figure, the red and the orange areas indicate the urban units, and the green areas show the leisure and the agricultural zones. So it is a map of Astropolis or of solar arc. One next, please. Yes, then some years ago, in the year 2013, we made a second improvement of the O'Neill concept. I made it in cooperation with Akos Bajor, an astronomer from the Vienna Institute of Astronomy. It was also published in 2013 at Springer's. The idea was to design a prototype asteroid colony, the near-Earth asteroid 2008 EV5. This is the one asteroid we have taken. It has a diameter of approximately 400 meters, and we proposed to force this asteroid into an Earth orbit beyond the Moon. After the mining of approximately 50% of the volume, a rotating toroidal colony would be built inside the cave. The diameter of the torus would be about 200 meters with a rotation rate of about 3 rounds per minute, providing 0.95 G. Because of the natural shielding by the asteroid hull, a lightweight structure made of of pneumatic elements would be possible. I think a population of about 2,000 inhabitants would have been possible. Next one, please. Yes, now I think we have to speak a little bit about artificial gravity. It is the simulation of gravity by centrifugal force. Now, first of all, we have to state that the effects of microgravity on the human body are loss of bone, loss of red blood cells, fluid shifts within the body, cardiovascular and sensory motor deconditioning. Now, if we build a rotating space station, it can provide up to 1 g of artificial gravity. And what is important, the bigger the radius, the better would be the conditions. Now, the second phenomenon we would have to discuss is the so-called Coriolis acceleration. It also occurs on Earth, a physical phenomenon which occurs on the surface of rotating bodies and causes a transverse motion of objects. It's also on Earth, but on Earth it's just winds and so on. So what you see on the right side of the slide is the so-called comfort box. It was developed by Mr. Jesko von Puttkammer, a former NASA engineer, and it means that a rotating space station should have a minimum radius of 30 meters and a rotation rate of 4.5 rounds per minute. Of course, nevertheless, here the bigger the radius is, the better it would be. Next slide, please. Okay, this is, and now we come to possible precursor projects for Island 1, providing artificial gravity. There is a project of the British Interplanetary Society. I think Jerry Stone is, I think, online. Hi, Jerry. Hi, Jerry. Hi. So, now the British Interplanetary Society proposed a precursor mission with inflated modules, which may be to a certain extent cheaper than modules from aluminum or hardcore modules. Yes, so there is a company in the USA which is, of course, working on such modules. And what you can see in this picture on the right side, if you look at the left side, at the figure 3, of course, one could test several levels of artificial gravity. Yes, so next slide, please. Yes, and now a second precursor project for Island 1, providing artificial gravity, is the so-called AGOS, Artificial Gravity Orbital Station, which could be a successor of the ISS, of the present ISS. It's a proposal made by myself and a colleague in 2017. Now, We took hard shell aluminum cylinders because the advantage of hard shell cylinders are, of course, they have the entire furniture and the equipment inside. A length of 18 meters and 7 meters in diameter. We could use, of course, SpaceX launchers, which are in part reusable. It would be a transport into low Earth orbit, which means about 450 kilometers above Earth's surface. Now, the assembly of such a station would be made in stages. The initial stage 1, there are 4 rotating living quarter modules which provide 0.9 G. There would be 4 zero gravity modules in the center, in the rotating center. And there would be, of course, also a docking module for spaceships. You can see it on the right side of the upper picture. Of course, there would be some connecting tubes and structural framework, which is necessary. And we thought about 1,600 square meters of solar panels. The total launch weight would be about 270 tons. The entire diameter would be about 100 meters, and the rotation rate would be about 4.2 rounds per minute. We concluded that there would be about 15 launches, including robots and so on, for the establishment of this Argos station. The crew could be about 24 persons. Then, of course, this Argos, this artificial gravity orbital station, is designed to be enlarged in stages, and at the figure right in the bottom, you can see the final stage of the enlargement. It is of course, it is a ring at the end, and it contains 32 living quarter modules, and the crew may be approximately 180 persons. So, next one, please. Next one, please. So, this is a question which I think everyone is interested a little bit. Where could the budget for exemplar Gracia Argos come from? So, at the left side, how much is the ISS in 25 years? As far as I know, the construction expenses are about $60 billion, if I'm right. The operational expenses until now are about $40 billion. So we can add the costs, the total costs, to approximately $100 billion, which means the expenses per annum, per year, would be about $4 billion. And now we compare it to the annual expenses for armament and warfare. Of course, these are, some data from the year 2018. Maybe now it's very much higher because of the war in Ukraine. 2 trillion. So, but of course, we see in the year 2018, if you if you add the expenses of the USA, of China, of Europe, and of Russia, you have $1,150 billion per year. So I think this is the source where we could get our budget for future space exploration and settlement. Make space not war. It is an idea from Adriano. He is sitting next to me. So thank you. Next slide. Thank you for your attention.
Thank you very much. So the paper is open for questions. You stay on stage, please.
Yes.
There are a few rituals when we go in the orbital station. The first one is on behalf of the observatory to give this beautiful book, Blick in das Weltall.
It's by Dieter Hermann, yes.
Yes, dedicated to Professor Hermann. And okay, so let's see if we have some questions from our audience, present or online. Any questions?
Yes.
So
Are there any questions?
Yes, so okay. Set.
Thank you. I enjoyed the presentation. I have to say, Jerry O'Neill was my freshman advisor when I was a student.
Wow.
But he was working on physics at that point and not space colonies. But there was a prediction by him and others who were working on this that by the 1990s, tens of millions of people would be living in rotating aluminum cans orbiting the Earth. What happened? I mean, you talk about money in the defense budgets, but that's a very false comparison because those will not be reduced. Those will only grow. The budgets you should be comparing them to are things like NASA, right? And NASA is $15 billion a year, so it can only be a small fraction of what's necessary here. Is it only money or is there something else?
Yes, I think it's also something else. I think there is how shall I call it, a shift in philosophy within the last decades, within the last, I think 40 or 50 years. So many people think we have, first of all, to solve the problems on Earth. But if we do so, we will never go to space.
Now, on this question, before I give the floor to Jerry, which clearly has something very interesting to say, what about a dual use of this orbital station? Also for the purpose of safety of Earth. We have a space force now in the US, we even have one in France. So could we use some of the compartment to ensure some of the safety of space? What would you see? And then ask them to pay for the bill.
Oh yes, I think we should move towards peace on Earth and not towards the military.
Yeah, so okay, so that's a big debate actually with Space Renaissance. We are really peaceful development, but to ensure peace, you have to prepare safety. So we could have a peaceful Space Force taking care of security, for instance, on this asset. Is that a technical aspect of security? Protection against, meteorite impact and other things, but also attacks, cyber attacks, and even pirates in the orbital space.
Yes, I think, for example, what I showed at one of my last slides, the station Agos could also contribute for some detection of near-Earth objects, which may be, of course, dangerous for Earth, for the Moon. So this could be also an alternative usage for such a station.
So now let's give the word to Jerry Stone, which you cited from the study that he performed with G-BIS. So
yes,
Jerry.
hi Jerry. Hi
Hello,
Jerry.
Jerry.
Hi, Jerry. It's yours.
Hi. Good morning from England, where it's just 9 o'clock now here. First of all, on the topic of defense spending and so forth, obviously, if we didn't have to spend so much time and effort and money on defense, then there is nothing else that we could not do, because we'd have all the resources that we ever needed for that. Frank White once said that space and war may be mutually exclusive, because if one of them occurs on a massive scale, then the other probably will not. But to really come on to the benefits of going into space, Gerard O'Neill, who I'm very pleased to say I met back in 1977 when he came to the UK, and basically this is what started me off on my fascination with space habitats. He's pointed out that we could use them to transfer a lot of the Earth's heavy industry into space. And as a result, this would mean we wouldn't need to be outputting pollution on the Earth. We would reduce the Earth's heat balance. And he was saying this 20 years before we all started really talking about overloading the Earth's heat balance. So he was really far in advance of his time. But he also pointed out that by sourcing the material from the moon and from near-Earth asteroids, that we wouldn't be mining the Earth for a lot of our materials, which would also be very beneficial to the ecology of the Earth. But there is so much material available in space that he said that nations would not have to fight each other for resources. And that, I think, it is something which is generally overlooked by most people who are been looking at information on space habitats, that by building these large constructions, the result, one of the main results would be a reduction in conflict here on Earth. And anything that reduces that kind of activity, and as part of the circle of that, it would mean that not as much would need to be spent on defense. That has to make this an area that really we should be looking at in much greater detail.
Okay, so Werner, would you answer to that? Having some heavy industry in orbital space?
Yes, it is also my idea since I think since many years, that we can put all the heavy industries and all the mining into space, and we can mine, thank you, and we can mine asteroids, we can mine our moon, and in maybe in some 100 years, we can mine also asteroids in the asteroid belt, and we can put, if we put the entire heavy industry into space, we can form a green planet from Earth.
So that's a very ambitious program, but step by step, okay, I mean, it takes quite some effort, money, energy to bring this material from Earth. So one good intermediate step is to bring it from the moon. It costs 50 times less energy to take something from the moon or from interplanetary space, trying to bring, indeed, an asteroid which has a right orbit and to park it around the Earth. So there are some possibilities for that with new technologies and also with clever use of the manifold, super highways that we have in the solar system, making use of multiple gravitational orbit. So, okay, very interesting topic, and that's a very direct transition to the next talk about manufacturing and emigrating by Jacob Müller. And Jacob is from Asgardia. Thank you very much. Yes, bravo. Thank you, Werner. And okay, we will have removed. So Asgardia space. So you are there now, huh? In space. I understand you are like floating in space. And so, what are you manufacturing? Thank you.
Yes, unfortunately, I won't be realizing a complete space colony that Werner has shown us, although I am a Minister of Manufacturing at Asgardia. But I can try to inspire you all, of course. So I'll try to do that via a presentation, and that's this one. Go. Yes, it works. Do you see the presentation? Very good, thank you. Okay, so my name is Jacob Mulder. I'm Minister of Manufacturing at Asgardia.space, at Asgardia, the space nation. And I would like to tell you a few things about manufacturing and about immigrating. Okay, that's this. And this is the logo of Asgardia. Okay, so these are the 4 things that I would like to explain to you. First, something about the space nation, then about my ministry, about a swarm architecture, sort of in the line of what we just saw, and at the end talking about immigrating. And I've got lots of things that I want to show you, so don't blink too much with your eyes. So first about Asgardia. It's a space nation. It's a real nation, an independent nation, and we try to pave the way for humanity to go to space. That's quite a challenge. That's a real nation with a real democracy, with a real parliament, everything, with a constitution, symbols. This is our flag, and an economy. And that's the most important one. We want to create a real economy in space. Okay, and to create all these things, of course, we need to have institutes and things like Asgardia TV and so on. And of course, Asgardia, the space, our website and so on, but it's about the country. And one of the things when you want to create a economy, then you need a business registry. So we've got a number of businesses registered in Asgardia. And of course, we've got a few other things like security, like research, which is of course very important for if you want to go to space, you want to know what's out there, how things work and so on. And one of those examples is the almost last line is reproductive technology, babies in space. Come back to that later. And the last one, the Institute of Standards, that's one of mine. And what we have in Asgardia is lots of people that believe in this dream. All around the globe, there's quite a lot of people that believe in this. We've got representatives all over the place. And like any nation, we have, in this case, 12 ministries, areas of development for all those various things that you have to do when you have a country. And we are a real country, and we have already a bit of territory in space. We do not have any land because we are a space nation. So we have a satellite in space, and that's our territory officially. But most important thing is we want to help humanity to go to space. That's quite a statement. So we are focusing, for example, on the birth of the first human child in space. And this business registry I talked about, and legal things are very important. We've got lots of lawyers in the group. that do think about that. And our constitution is about equality. And it's not about geopolitics, but it's about space. So we talk about astropolitics. And this is an example of things that we talk about. We want to talk about this space child, and therefore we need to have radiation protection and artificial gravity. And that has already been talked about by former colleagues that did all the presentation before us. So this is just an example of a logo of the things that we are working about. So, okay, that's about Asgardia. So do go to asgardia.space to have a look. But now about my ministry. It's about manufacturing, but we of course already have quite a large space industry, which creates nice rockets, reusable stuff, half products, services, everything. So there's already a lot out there, and the idea is that Asgardia, as the space nation, should be able to integrate and orchestrate things and join those services, and that way we can collaborate and integrate things together. So, because we want to implement all those things, we want to create an environment for that, for this industrial growth, and for this integration, for this integral approach. And as my Ministry of Manufacturing, I would like to lay a proper foundation for that, so that we can prepare those things, so that we have a basis on which we can continue. We as a humanity, that is. And so foundations, you need a few things, like, for example, let's first define a few standards. There are, of course, standards, but for example, there are things like meters and yards, centimeters, inches. Oh gosh, we should define a few things before we make mistakes. And once we have defined those things, we should check those things. We should have a manufacturing approach to do that. If we standardize the way that we work, we standardize the way that we do projects, it would be easier to integrate things. It would be easier for us as humanity to work together. And when we've got all those things, we can facilitate and promote that approach of integration and so on. And for example, create a large marketplace for things. That would be typically something that Asgardia could host as being the space nation. This approach will be, of course, is about integrating, about components, products, and services, putting those together, gluing those together, and not doing that because we need to and asking money for it. No, we want to do it in a business way, focusing on multiple markets, and all of those things will be services. And of course, all of those things have to be modular and agile and so on, because that way you can combine them and integrate them together. Of course, the results should be robust, because we're talking about space, which is quite a hostile environment. And it should be really secure, because there will be people out there. Information security is important. So this approach, we do that with small steps. Of course, we cannot change the whole world in a year, but we can do it in an integral approach, looking at all those aspects and celebrating successes. That's very important. We are all humans. We want to celebrate things when things go right. So those things are very important. Okay. That was about my my ministry, and then about an idea that sort of is in the same area as where, for example, Warner and Jerry were talking about, settling in space. Years ago, in one of Asgardia's conferences, I presented a architecture for a space colony. And the word that I use a lot is the word swarm, because I think we need most of the things that we already saw, for example, this morning. We need all those things combined together. We need multiple things. We need a swarm of things to be able to live in space in a sustainable way. So multiple habitats, multiple things, not only for living, but also for manufacturing, for commercial stuff, to make money, and of course for science. So how do you do that? This is a lot of things. I won't go into all these details, but the idea is that we have multiple stations, and we've got also stations on the Earth, on Moon, on Venus, and so on. Why not? And we need a swarm to protect those things from incoming objects and those kind of things. We also need a swarm for repairs and small modifications. We also need a swarm for logistics and for energy services and for all kinds of things. A number of swarms all working together, an armada of things. And of course, this whole armada should be coherent and sustainable as a group, as a swarm. And of course, that's why we need an architecture for that. And how do you start? Well, with this picture, we already saw this one yesterday. And Maslow's hierarchy of needs. You start at the bottom and with things like air and water, because we need those things as humans, because we want to go in space. So we really need things like food and shelter and so on, basic things. Think about those things. If you have enough energy, if you really have enough energy, abundant energy, then you can do really a lot. So maybe you should start with that. Even before you start with air and water, before you even go with talking about humans, maybe you first start with really lots of energy. Okay, so this architecture, it's all about circularity, of course. Yeah, so and that's quite a thing. That's one of the reasons why we talk about those things a lot in Asgardia. If we have such a settlement out there and somebody dies, that will happen if we live over there, then what you always see in science fiction is that they sort of have a sort of a burial and they sort of send that person, the body, to space. However, we should not do that because it should be circular, and that's philosophically quite something, that you reuse the body material, and that you really think about things like abortion and euthanasia and so on. Those are very serious things when you go live in space with 20, 30, 100,000 people. So you need a really integral approach, also looking at those things, other psychological things. So you need a multi-layer architecture for this whole swarm thing. And you should start with standardization. You start with this manufacturing approach, and that's why we had this thing in my my ministry, of course. Okay, how do you do that? Well, you just don't launch such a large O'Neill cylinder, but you start with building things on the moon with those 3D printers, with sending them to space with this magnetic launch system that was already shown with the previous presentation. And then once we have things, manufacturing complexes in space and swarms around them with semi-autonomous entities, you can use robots and sort of autonomous entities for that. And we already have those things in the military. So we need to use those things from the military for our peaceful use. And of course, all the services, the sustainability services and so on. And in the end, why not? We can, of course, also, for example, get propulsion material from Venus. Why not? Let's think big. And all of the things that I'm talking about are all services. You've got manufacturing services, energy services, habitat services. And the nice thing about services is that you can sell them. You can buy them and sell them, and you can make a profit. So I don't want to ask for money. I want to earn money. We should earn money, all of us. We should not ask money from whatever, from NASA or whatever. No, we should do like Musk and Bezos are doing. Make money out of those things. Make money out of integration and so on. We should create, that's exactly, of course, what we are doing in Asgardia, in Space Nation. The space economy, not on Earth, but also on the moon, on Venus, on the Moon Village Association. Those groups, they work with real economic things. They work with business cases. We should go in that direction. I'm talking about business things because that's where I work in normal daytime. I'm Minister of Manufacturing, but I'm also I'm also working in daytime as CGI. I'm an IT security and enterprise architect at CGI, which is one of the largest IT multinationals in the world. And they work and they think in the same way. We want to create very nice things for our customers, for humanity, but we also want to make money out of that. Why not? It's not a bad word, finance, profit. Why not? And then Asgardia being sort of the glue that integrates all those things and that provides the standards and so on. Okay, then about immigrating. Now it's going to be fun. This is me. You can't see me that much, but I'm in an electric reclining wheelchair, and I've got issues with gravity. So I really want to go to space because I've got issues with gravity, and in like 15 years from now, I will have more problems with my back, and the problem is in my back. Gravity squeezes my spine. So I need to immigrate to space. Not only I want to, nay, I need to. So you will help me with that. It is a self-fulfilling prophecy, I know, but it is doable. I've presented these things quite a few times. And everybody that I talk about, they say, okay, in 15 years, well, if you look at it in a commercial way, it might be doable. If Musk and Bezos and so on continue, and if no real disasters happen, and that we get a nuclear war or so, then it should really be doable. And you guys are thinking in the same line. We are here, this conference, this meeting, and people watching at YouTube, we have the same dreams. We share those ideas. We all want to go to space. We all think that those things should be possible. Otherwise, we would not be here. Yeah. So you are all going to help all of us. We are all going to work with Asgardia, with all those dreams, because we can do it. Yeah. That's a German expression. Wir schaffen das. Why not? Okay. So conclusion. Space Nation, it's a dream shared by many. We are paving the way. Really. We have a real nation. Everything is working. A real democracy. Coming weekend, starting this evening, we will start another digital session where we will accept a number of new laws, for example, in space. Yeah, of course, we are working at the moment in Earth, but okay, we are creating those laws for space. Starting this evening, we are really currently working on those things. We want to help humanity to live and work in space. And of course, we need really experts. So you guys, we need you guys. Sorry, ladies too, of course. Sorry, I no. I didn't mean it in the wrong way. But we need everybody. We need people. We need smart people, experts, also artists, also philosophers, also poets. Why not? We need all those people because we need all those smart minds, open minds to do this, to make this giant leap. So very simple. Go to asgardia.space, and there's the figure of 1 million over there. We already got quite a few people. Join us, become a resident. Go to this space, look at all the things that we already did in this thing. And this is one humanity, one unity. It says there on the top in this figure, one humanity, one unity. If you abbreviate that, you get OHO, OHO, and that's our greeting. So I say OHO to you, and thank you for your attention.
Okay, thank you, Minister Jacob. Yes, so we are going to call for questions. For instance, so do you have some architecture concept to show, and also a timeline for how it can be put in place? These manufacturing facilities?
Well, the architecture, of course, I only had 20 minutes, so I showed 1 or 2 slides about it. And of course, there's much more ideas behind it. And the timeline is, well, it depends on us. Mm-hmm. It depends on how we can collaborate, how we can internationally share our dream, and all those great institutes like the SRI, like the Moon Village Association, like the Mars, and so on. All those institutes that we talk about, we should all collaborate. We should work together, because together we have all those great minds, and together we can work. And I really believe in this 15 years. I have to, because I personally have to, but it is really possible. Everybody that I talk about, and that I go to more like conferences like these, and they say, well, yes, 15 years, it should be doable. We won't have those large O'Neill cylinders like with a few of those each with 20,000 people in it or so in 15 years. That's a bit too much. But we will have hotels in space by that time. I mean, people want to buy tickets for those, and there's quite a few billionaires, millionaires that really want to spend money on a ticket for marrying in space, getting a child in space. Why not? There are lots of people that want to do that. Not only go to Mars, but also do those things in space. And there's already space tourism. That's quite a serious business already. So why not?
So,
Think big.
a question. So, you have currently Asgardia 1, a small satellite. So, what is the next step that is going to happen in the next year? Are you looking at some modules that you could put, or will you also attach some of this to existing space station?
Well, that would be nice, but there's already quite a few people doing those things. So we don't want to compete with those people. We want to collaborate with those people. So let's start a bit more in the basics, a bit more on the foundations. Let us define a few standards, define a standard approach and so on. Let us build things up from the start, because if we make such a good foundation, then we can collaborate really internationally. If you look at the large systems that we created, like CERN, like the Square Kilometre Array and so on, those are huge things that humanity has done. And the only way you can do that is by international collaboration. So let's first make this basis of this international collaboration and this digital democracy, for example, and all those standards and so on, that international collaboration. Let's work from the bottom, and at the same time, let's unite all those great minds in this room and across the world.
Mm-hmm. Okay, so that's good. So on practical side, I mean, we have a nice concept that Bernard has presented, and we are putting together a working group on this at the Space Renaissance. So we'll be happy to share our concept, and if you can help us to build this, yes, let's do that. Okay.
Very good.
Yeah, perfect. So thank you very much, Jacob. So, okay, now we are, yes, on time for our space coffee break. Yes, so, and we'll reconvene in 20 minutes exactly for the talk on the gateway concept. Okay, let's have our coffee in orbit.
So how was the coffee?
Well, we're back. Let's just start without him.
Yeah, let's do that. Why not? Yeah, it's always a thing when you have a hybrid conference. You can't see the room. You don't know how many people there are. The only thing you can sometimes hear is the amount of people that applaud, but that's about it.
Yeah. Well, I really wanted to be there. I've never been to Berlin, and it's such a great city. I've been to Frankfurt a million times because I used to be an airline pilot, but I never got up to Berlin. And I was thinking, oh, this is my chance to go, but it just didn't come together at the last minute. So got to do this virtually, which is really nice. I like being able to do things virtually because you can bounce around the world quickly. But to be there though, and everyone's so tired of COVID. We've all been locked indoors for too long, and it's time to get out. And all this came up.
Yeah,
I was excited about it.
And it helps when you physically come together. Then you can talk with coffee. Yeah.
Yes.
In the hallways, whatever. So that always helps. There's lots of discussion going on over there.
Yeah, you're right. Yeah, and it's important to spend that time with people in the industry to get to know what they're thinking beyond just the presentations. Yeah, I agree. I've attended quite a few conferences, and I really like doing that. But I haven't gotten over to Europe as much as I want to. It's easier, in California to go up to Washington State or something like that. But getting over to Europe, which is always more fun, it's a little more difficult to get there. And I guess this summer, anyone trying to get out of an airport is having a really hard time. The air traffic control is all messed up over here, and the airlines are all understaffed. It's just a big mess.
Same here. Yeah. Yeah, the understaffing is a general issue, I think, for quite a part of the world. Yeah. Also here. Yeah.
Yeah. So
because my computer was
good. But we see we have established a connection. We are Space Asgardia colleagues, but also with some of the Earthling. And we have as well some from other worlds that are equipped with beautiful geodesic architectures, we can see. Okay, so please, Adriano is going to beam us up, connect us, and we are ready to broadcast in a few milliseconds.
Yes, I think we are broadcasting.
So you are back. Yes, we had a blackout for 20 minutes. It's called a coffee break. And now we are back in communication in this second day of the Space Renaissance Art and Science Festival, and second day that is dedicated to astronauts and civilians, Science and Technology Day, oder Astronauten und, okay, Astronauten, Wissenschaft und Technik Tag. So the next speaker now in the session that is presenting a number of concepts for space as well as Moon and Mars habitat is John Blinkel, and from the Gateway Spaceport organization, he will explain the gateway concept. Are you with us, John?
I am with you. I'm here. Yes.
Excellent. From the gateway already, the first module?
I'm sorry?
Are you already in the first gateway module?
No, I'm not there yet, but we're
Almost
working on
there.
it for sure.
Yes.
Yes.
Okay, the floor is yours. We have a presentation from John already that was pre-transmitted. Yes, the floor.
Do I have your presentation or will you share your screen?
Yeah, I'll be sharing with my screen.
Okay, so you will share directly from the gateway. Okay,
Yeah.
the floor is yours. Thank you.
Yes, thank you. Thank you. Okay, let's go here. And let's get the view up to slideshow. Okay, there we go.
That's good.
Looking good? Okay, good. Hello, everyone. My name is John Blinko. I'm president of a small company called Gateway Spaceport and CEO of Off-World Industries Corporation. I would like to thank Adriano and Professor Foyne and Sabine Heinz for inviting me to this prestigious event. It's a pleasure to be here with you guys again, like I was last year. This is very exciting stuff, what I'm going to show you here. So I'm just going to jump right in here. This is the Sargon construction ring. It is designed to build big torus type stations very fast. Sargon will not be easy to build, but once completed, it can build lots of big stations that will be affordable for people like you and I to visit. For those of you who have not met Vera, let me introduce you. This is Vera Station. It is a 2 torus rotating station design. The outer torus is 220 meters in diameter. The inner torus is 84 meters in diameter. The core diameter of both tori is the same. It's 24 meters. That's a lot of volume. Vera stands for voluminous environment, rotating architecture. So, how does Sargon build Vera Station? Vera Station is made up of thousands of panels made of aluminum alloy 2219-T8, the same stuff that the International Space Station is made of. Each panel has a base layer of whole metal that is 5 centimeters thick and protected with Whipple shield on the exterior. I can hear someone has a live mic. If you could please mute that. Okay, move forward. These panels are formed into rings, and the rings are welded into place all the way around until a torus is formed. This, what you're looking at right here, is a panel ring. This is a panel ring as part of a torus. The inner torus you see here is made of 84 panel rings. This is the Sargon construction ring building a panel ring. If Sargon can make 1 panel ring every day, then Vera Station could be built in only a few months. But we have confidence that Sargon systems can build 1 panel ring every hour. These yellow box-like structures are magazines that hold the panels. This image has a magazine with one side removed to show you that the panels are loaded inside of it. The black box on top is the battery. It should be white. This is an old image. And the big skateboard on the bottom there on the rails is a panel cart. It goes under the magazine and picks up a panel and then takes it down the rails to the weld ring to be welded into place. The weld ring shown here is where all the panel seams are welded together to form the next ring of the torus. Both vertical and horizontal seams are welded as depicted as here. That's the weld ring right there. The magazines are on to the left of it. Here we see the weld ring with the vertical and horizontal welders. I know this may be confusing to you guys at the start here, but it kind of all comes together at the end, so bear with me there. Here we have a weld manifold with a model 4210 Kimball Physics weld head. The weld head can traverse the whole seam, of course, but it also has some lateral translation to track the seam accurately. While Sargon Construction Ring is building the station's hull, other Sargon systems are building interior structures. Here we see a pod delivering a load of floor panels to a floor building machine inside of the half-finished torus. How do the panels get to the orbital construction site? Starship will deliver the panels and supplies every day to keep production moving. The panels and the batteries arrive on what we call a materials tree that unloads itself from the rocket. A pod, which is what you're seeing here on the left, takes a stack of panels and then loads the magazines. This here is an empty, oops, let me go back to that one. This is an empty materials tree, which maneuvers itself back into the Starship to go back down to be reloaded with recharged batteries and more panels to build that, to continue building the station. Sorry, that's one of my cats there meowing in the background. We have no interior images yet. Those are coming, but this floor plan gives you an idea of just how big Vera Station will be and how it can accommodate 900 guests in the outer torus with ease. Those blue pegs that you're looking at there represent a person 2 meters tall. This depiction shows a large open area for sports events or live concerts. Vera Station will not produce Earth gravity, but instead for lunar gravity. We think that'll be a lot more fun. This is an artist rendering that came from an online game, but the image was used here because the windows are laid out about the same way that we have our windows laid out for our station design. Here's another image of the mezzanine hallway. The windows, once again, a little bit bigger than ours, but this is kind of how the layout of Vera Station is designed. Now, this kind of ends the review of what we had to show you from our first video, which has been out for a couple months now. And now I'm going to preview to you what is coming in our next video, which is called the business case for Vera Station. These steps towards building Vera Station, this is a list of all the steps here. Only the first step at the top here, the ground demonstrator, offers no ROI, return on investment, which is important because if you can't make money trying to do something, the investors just won't come in. These are the steps toward building Vera Station. The ground demonstrator offers no ROI, but each step after the ground demonstrator, excuse me, can yield substantial profits. And we'll just kind of go through some of those designs that we're talking about here. This is Virgo module. This module would be built using the 14-meter Saigon construction ring. We will build them for customers looking for larger off-world habitation. This module offers over 4,000 cubic meters of volume. For comparison, Destiny module on the International Space Station, it only offers 104 cubic meters of volume. All of ISS gives us 900 cubic meters. This module is an entire space station. Is 4 times the size of ISS. That's why we have coined the term a station module. We will need to build one of these modules for ourselves to help us build Vera Station's 24-meter Sargon construction ring, and then the big STVs that will service that. And we'll get to that next here. This is a quad of Virgo modules all put together, which would offer 16,000 cubic meters of volume. We call this massive station ZG station. The Virgo module is the basis for our STV, Station Transfer Vehicle. Starship has 1,000 cubic meters of volume. That's more than a 747 that I used to fly. To handle everything that Starship can bring up, we need a big spaceship to transfer all of its people, luggage, cargo, and more to Vera Station. This STV will have about 3,000 cubic meters of usable volume, plenty for all of Starship's payload and for the next generation of bigger rockets to come. Now, this next image is blank. I was waiting for an image to show up of Valhalla Station. What is Valhalla Station? It is 4 of those big Virgo modules all joined together as in one module. It would actually save on time to build it and costs and so forth. I apologize for not having the image. My graphics guy couldn't get it to me in time, so I can only tell you a little bit about it. The Virgo module station module would be a popular choice for those who probably want to do production, but it could be a mixed use station also. I promise I'll have it to you guys next time. Okay, the last step before building Vera Station would be this here. This is what we call Vera IT, which is the inner torus. It could operate as a standalone station. This smaller Vera Station will be a copy of the full-size station in almost every way, yet it will allow us to learn how to optimize the customer experience in a smaller format before a grand opening of having the bigger station a year or so later on, where we add the outer torus to it. Okay, after you go through that whole 7-step program where you're building your way up and you're learning to use Sargon machines and so forth, you're ready to build the full-size Vera station. This would be spinning for lunar gravity. It would be able to accommodate over 900 guests. It would be basically a hotel in space. And we're looking at a 3-tier pricing system for people to go to this station. And last but not least here, I believe that Starship can help us build out the inner planets of our coming solar civilization. And Sargon systems could construct the habitats around these worlds. Imagine having a large rotating spaceports around Venus, Earth, the Moon, and Mars, and more rotating architecture would follow on the belt too, of course. I think with space construction tools like Sargon, it is inevitable that we will become a spacefaring race. The alternative is unimaginable, but it's possible. Now, I have a little video that kind of puts everything together for the construction. I hope it'll work here. We'll give it a shot. Let's see if we can get this going here. Here we go. All right, that's it.
Thanks very much. Quite an impressive concept and visual as well. Yes. So how do you see the time scale and okay, the roadmap for implementation?
Yeah, well, that's why we have that 7-step program to build up to something that large. The big station is down the road. The first things that we would build would be the modules using the same type construction ring. This panel construction, this new technology can build things rather quickly, but there's development time that I don't talk about or show you here in the video. We're showing everything coming together quickly. Development time for that machine, it could take years, but it's worthwhile investment because once you get that process working, it's designed to build things quite quickly. And it's scalable too. You know, you can go from modules up to toruses. So it has a lot of potential.
And okay, for the question, I see mostly you have a prefabricated elements and you insert and integrate them. So do you have also some deployable or inflatable or other soft device that can increase the volume?
It's a hard shell station is what it is. And then when the module's being made the same way, they're using the same aluminum panels. Yeah. We're shooting for something that's more durable in orbit, looking for longevity of whatever we're creating. And also, especially those STVs, you know, they're going to be docking with the station quite a bit. They're going to have to be rather durable also, like the old 747 I used to fly.
Oh, Jacob, yes, you have raise your hand. You have the floor.
Yes, I'm of course very enthusiastic about this. So congratulations! I love this. This is very much in line with the things that I talked about, of course. So we really need to talk about a lot of things, including the modular approach and the integral approach. And so I love it. I'm a fan.
Oh, thank you. Thank you. Yeah, I'm excited about it too. I think it has a lot of potential.
So what would you see for the first phase? What is the level of investment that you need to get a first phase running?
Yeah, the first objective is actually rather quite small and it's rather affordable. It's a ground demonstration. Electron beam wellheads, like you saw there, they operate in vacuum. So in space, that's a natural environment. But down here, we're going to rent some vacuum chambers to do some welding. Now, welding is necessary, is not anything new. It's the positioning of those panels exactly right so you can start welding. Because the tolerances for electron beam wellheads is it's 0.005 inches or 0.127 millimeters. So you have to be able to position your panels exactly right for the weld head then to bring those seams together. And that's where we have an engineering challenge. And you have to do it in an automatic fashion too. Most electron beam welding down here on Earth is kind of set up manually, and that's not what we're after. We want this to come together in an automated fashion, so it can happen. You know, so you can start doing it faster and faster. So that's where we have that a long timeline for the engineering and the development time, is getting those first steps down.
Okay, very interesting. So I think that, and I hope. Can you give me a book? I hope you will have also in your habitat and all the habitat we have seen, a library as well, because we have a gift for you. We want to put you this book, Blick in das Weltall, that we give to all our speakers. It will have its good place in the library in orbit, I suppose. Excellent. So thank you very much. Let's get an applause.
Thank you.
Now we move to the next talk. It's about Selenopolis, the Erike concept, and the speaker is Adriano Ottino, so Space Renaissance founder, vice president, and ambassador.
Okay, let me take my presentation. We also exchange it.
Good.
So it's always tricky. The camera.
Yeah, can change.
I succeed. Integrated camera. Yes.
Good. Okay.
I'm here. So my presentation is here. I have to share it.
Everybody hears it well? Sound? Good? Sound check? Visual check? So, okay, so Adriano.
Yes.
Very good.
I'm coming. Un momento. Where is share screen? Okay. Okay. Are you seeing my presentation? Yeah. Okay. Good. I have to make a premise that I am fully in agreement that the on-air model for habitat is maybe the best that we can conceive, because it solves the problem of artificial gravity and it solves the problem of protection from cosmic radiation. Of course, with the improvements that Werner showed us in his presentation. And even better if we succeed to take a big asteroid and dig it inside and make it rotating to have an improved on-air concept. However, having said that, I am presenting the point of view of Kraft-Ericke. Kraft-Ericke was a supporter of the lunar development for industrial reason and for habitation. Selenopolis. I think a Kraft-Ericke view is paramount important, because of course, if we don't know if we will use to live on the surface of the moon, for sure we have to work there. We have to mine the moon for resources, we have to make industrial settlements and so on. So it could be a combined way to inhabit in on-air modules and go down to work on the moon for shifts and then go back to modules. Okay, it would be open to the. Why I'm not showing myself, but I'm showing James. Okay, never mind. So okay,
It's on. It's on.
hello, better. Okay, let's start. So, lunar industrialization and settlement, birth of a polyglobal civilization was called by Kraft in 1980s. So, scientific and evolutionary facts leading to definitive justification for why man must industrialize space, changing our present closed world into an open world. Three interlocking phases of open world development will be exo-industrialization, exo-urbanization, and extraterritorialization. A lunar development strategy consists of 5 logical development stages. DS1, involving further synoptic prospecting for mineralogical provinces and candidate base site. DS2 establishes a circumlunar space station, moon ferry, and automating laboratories and pilot facilities, including an oxygen extraction plant from the surface. DS3 establishes the first generation nuclear-powered central lunar processing complex, and the first large-scale industrial production begins. DS4 diversifies productivity by adding feeder stations in more distant metallurgic provinces, and DS5 establishes Selenopolis as self-sustaining lunar civilization founded on a powerful fusion energy base. Okay. So the central conclusion is the mandate for low-cost transport and energy, early self-sufficiency, early investment return, industrial flexibility, and a systematic approach to creating a positive Earth-Moon balance of trade. The extraterrestrial imperative and lunar development that were concepts that were developed by Kraft-Ericke, 3 evolutionary phases of our expansion into space, following initial exploration can be substantiated as space industrialization, space urbanization, and extraterrestrialization, prolonged process of socio-psychological development and anthropological divergence based on the integration further evolution of the first two phases manifesting itself in the physiological, anatomical, immunological, aesthetic, and general cultural sectors. We should concentrate on the industrial development of space in the post-Apollo era. First in near orbits with commercial transportation and small space facilities, then on the moon. So Kraft-Erike wrote these things in the 80s. So it was the post-Apollo era. And now we are 40 years after that. So the delay is huge. In this paper, Erike is basically talking about the moon industrialization is first of all the logic of lunar development. If God wanted man to become a spacefaring species, he would have given man a moon. Similar to Earth, the moon, despite all differences from Earth, still bears closer resemblance to Earth than do any other accessible surfaces in the solar system. The moon is the logical proving ground for subsequent industrial developments and settlements as well. And it is a kindergarten, only 2-3 flight days away. It allows us to develop at our very doorstep the experience we need to operate successfully and cost effectively in more distant regions. The moon effectively permits the development of the habitats, material extraction and processing methods, and in essence, all the science, technology, and sociology required for a responsible approach to extraterrestrial operation. So, there was a big discussion in the past years about the moon versus Mars. Nowadays, I think this discussion is a little bit lower, and everybody seems to concur that we need to go to the moon and to Mars. And that maybe going to the moon is a milestone to go further. The point of Kraft-Erike is choosing Mars over the moon as the first location for extraterrestrial development would take more time and money. We would first have to develop a new propulsion system. The development of adequate heliocentric transportation would be an enormous investment requiring additional acceptance of the high costs and operational risks associated with a more widespread launch window and longer transit times that still cannot compete with those of lunar flight. Moreover, we already have most of the technology required to get to the moon and back. We don't need much more than oxygen hydrogen propulsion, especially since we will be exploiting lunar oxygen. A few comments. Are we really constrained to choose between moon and Mars? Both are urgent. Industrializing the geolunar space region is priority. Reaching Mars and investigating its natural scale, thinking about absurd military expenditure as Werner already said, our global leaders shouldn't really ask us to choose between moon and Mars. If we spend $2 trillion per year in weapons, I wouldn't say, okay, I wouldn't say anything about that. We could afford for sure to spend a few tens of billions more on civilian space technologies and projects. So, Erike versus Monet. A lunar industrial facility will process lunar material in situ, precluding the need to transport the large masses of raw materials for processing in orbit. The weatherless lunar environment permits open storage of elements not immediately needed. This is preferable to the problems of mass distribution, orbital control, etc. The stored surpluses would present to an orbiting facility. The high vacuum and low gravity offered by the lunar surface are two key advantages for extraterrestrial industry. The high vacuum facilitates the generation and maintenance of cryogenic temperatures, and 1/6 gravity provides benefit for construction, transportation on and beyond the moon, and operation. Where 0G is required, easily accessible circumlunar factories can be used. The energy to deliver cargo from lunar surface to orbit is less than 1/20 of that required for transport from Earth. So these were the Kraft-Erike arguments in the discussion that was going on in the 70s and 80s, of course. Many of these could be maybe superseded by some of the already available technologies.
Let's think about the SpaceX Starship and other things. The Moon industrial settlement, however, it is worth to note that Erke always is talking about industrial settlement more than habitation. The Moon industrial settlement, technofield lunar environment is favorable for powder metallurgical technology, electron beam and laser beam evaporating welding, and other advanced efficient manufacturing processes. It is also favorable for the application of nuclear power, which is needed for the productive process to continue throughout the lunar night as a precondition for the economic viability of lunar operations. On the Moon, protection from cosmic radiation is offered from a space angle of at least 2 times by the lunar mass. Loose lunar material to provide protective shielding is abundantly available in situ. Lunar sand, breccia, and dust constitute suitable construction material. With a surface-based establishment of large hydroponic agricultural facilities is also possible using lunar bulk material enriched by nutrients imported from Earth. The Moon offers a cost-effective, flexible, stepwise approach to the 3 fundamental subspheres of an extraterrestrial settlement: technosphere, biosphere, and sociosphere. So, the case for Moon, provided by Graf-Derike in summary, is the Moon is much more than a quarry for orbiting facilities. It is a logical target for open world development with a significant technological, productive, socio-economical, etc. consequence potential. Open world development will involve a difficult trial and error process that must progress in steps. The lunar environment is protected, conducive to stepwise development and experimentation, and forgiving of failures. The Moon is the logical first target for open world development on which we can cut our teeth relatively conveniently and economically. Therefore, large space habitats, which I call androcells, follow rather than precede lunar development. Their purpose is different, serving primarily as links in the development of other solar system worlds. So, my comment, Erica was not against her name, he just wanted to come first. He wanted the lunar development to come before the androcells. The principles of the Moon economy, lunar development must be rooted in a viable lunar economy with favorable, sustained cost yield prospects, so that venture capital and private independence-oriented investment can be attracted as rapidly as possible. Keep investment sizes manageable, assure minimum non-productive freezing and of investment capital, contribute to reduced operating costs, especially logistics from Earth. The independence-oriented investment will involve use of nuclear energy, primarily for power supply rather than for transportation, reduction of terrestrial propellant supply through transportation, energy management, lunar oxygen production, and lunar deposits on the Moon and the relevant orbits, especially geosynchronous and near-Earth orbits. Extensive use of lunar materials for construction, for shielding, growth of food plants, and other purposes. In summary, maximum value generation capability and flexibility should be achieved with minimum initial expenditures and lead time. Lunar products are a very, very long list. If you look in the Erika paper, you will find the development results will result in a lunar industrial output, including raw stock from mining and refining, as well as a vast number of semi-finished and finished products. Sheet metal and trusses of aluminium, magnesium, titanium, iron, or alloys. Castings, bars, wires, powders of pure or alloyed materials, glasses, glass wool, ceramics, refractories, fibrous and powdered ceramics, insulation, conductors, anodized metals, coatings, including almost perfectly reflective sodium coating. Thin film materials, silicon chip, solid gels, and tire structures of various materials and alloy for lunar and orbital installation. Okay, I will not read the whole list. It's quite huge, but however, it is in the presentation and can be, and of course in the paper. by craft, so it can be consumed anytime. Primary markets are, of course, lunar surface, geosynchronous orbit, near-Earth orbit, and Earth. So for domestic demands on the moon, for industrial and habitational development, new forms of entertainment for terrestrial TV viewers, tourism and retirement environments for terrestrials on the moon. Geosynchronous orbit, by 2000, it was foreseen by Cluster in 84. There's only well over 1,000 services, satellite that will be virtually indispensable socio-economically. Spacecraft servicing, replacement part, new components, salvaging and recycling of the operating systems that is important for space debris and refugees reused. In addition, lunar oxygen filling station might be established to reduce the cost of managed access to supply deliveries needed from Earth. Okay, and so Earth will be a customer too. Major market for lunar raw materials, semi-finished products, and space-made components in large quantities, involving large masses that will be handled economically. The raw material should first, if the raw material should first have to be supplied from Earth to NEO and the manufacturing facilities. These lunar imports will sustain industries and create new job markets on Earth. So, lunar development strategies should be viewed, the lunar industry should be viewed as an organism that over time evolves to progressively more complex capabilities and generates sufficiently strong foundation for expansion. Lunar industry must be broad-based and diverse if it is to last. The need for economic feasibility and early returns will require a skillful interplay between market customer-oriented products and services and infrastructural investments such as transportation, energy, and surface-based integration that expand food production and diversify industrial productivity. So, the guiding principles will be low-cost access to the lunar surface, ample and low-cost energy assurance, early self-sufficiency, and industrial flexibility. The 5 stages, envisages five main stages. Consist of 2 basic components: the lunar industrial zone and the lunar industrial space installation. Now, the technological approaches to lunar industrialization consist of lunar development, 5 development stages, and there is an associated economic and industrial rationale for the transition from one DS to the next. So, 3 main sectors: technosphere, research, technology, industry; biosphere, plant, animal life, food production; and sociosphere, habitats, living and working spaces, society, economic, politics, and culture. So let's go through quickly through the stages. The development stage 1 could be accomplished in this century. That was, for us, it was the past century. It involves synoptic perspective, simplified surveyor-style landers, and at least 1 lunar polar orbiter. Emphasis should be placed on sites in the western and far western part of the near-Earth side, north and south, as well as at the equator. This area holds promise as a base site due to its potential for resources, its ready low-cost air communication and transportation accessibility, and the flat area between 50 and 60 degrees western longitude at oceanus crossed area. Suitable for a slight landing strip, which would in turn influence the location of the first central lunar processing complex in DS3. DS1 would also include establishment of a lunetta reflector orbiter to illuminate the perpetually shadowed places in the high latitudes and the polar region to permit photography, cartography, and the possible identification of polar ice deposit. So, first generation lunar surface in the development stage 2. First generation lunar surface crews get started in laboratory habitat models made from Earth. The inverse converging shape of the modules maximizes the shielding against corpuscular radiation, optimizes temperature control for placement in equatorial regions, and serves as an umbrella to provide shade in the module's immediate vicinity. So, development stage 2 will be surface-based selection and preparation. Preparation phase for the first generation ground personnel. Surface-based site selection and operation training prior to lunar-based build-up. The components will be a circumlunar space station, CLSS, at 100-kilometer equatorial orbit using a moon ferry for manned surface missions. It serves as habitat, operations and training center, laboratory for engineering, biological and medical purposes. Experimentation with much larger quantities of lunar materials brought by automated returners. Selection of the appropriate surface-based site about halfway through PS2. Experimenting medical and behavioral life on lunar surface and space station remote from Earth. Establishment for sophisticated automated laboratories and pilot facilities on the surface. Using the enough CSS personnel mission to set up, start and maintain the systems. The first small-scale automated oxygen extraction plant, providing gaseous oxygen for NF and CLSS. Modules placed on the moon for personnel to stay on the surface for weeks at a time. These two must be accompanied by major strides in research, development, testing, and engineering of special, highly cost-effective transportation system for use in later DS. DS3 will be the lunar industry kickoff. Return of initial investment begin here, demonstrating creditworthiness and attracting major investment from Earth for next stage. Cynthia, a nuclear-powered central lunar processing complex installed in the Oceanus Procellarum at Ecuador. Cynthia will first produce oxygen and other materials. Construction works, cold welding, cut lunar rocks, producing lunar bricks and possibly cement with lunar silk as binder instead of water. Compacting lunar tines from powder into cold sandy material into building blocks for lunar igloos or better ligloos. Ligloos will have sprayed hard-tight inner liners and iron, providing shelters, workshops, and greenhouses for growing food plants. Still on the S-train, we will have robotic welds, cold welding, laser and electron beam welding, surface mining and drilling, monitor and maintain a wide variety of equipment and agricultural models. And the Cynthia production, there will be oxygen, silicon, aluminum, iron, glasses, and other materials, then powder metallurgy, vapor phase metallurgy, solar cells, computer parts, spatial structures, and so on. Novel transportation arrangement to radically lower the cost to from lunar surface and across cislunar space. CLSS grows into a staging base, training the second generation astronauts and expanding into a zero-G factory. So, moon mining, processing, during the S3, the first street mining, beneficiation, processing, and refining facility will be established as part of the CRPC called Cynthia. Material mined on the surface is sorted and fed into furnaces. Raw materials to be refined and are removed to be processed for transport to CLO and further processing at zero gravity. Some can be exported to customers in Earth orbits and on the Earth. DS4, the lunar industry expands, differentiates and grows beyond extraction and semi-finished products to our finished products and assemblies. Cynthia is connected to feeder station previously identified for abundance of certain raw materials. The feeder stations are highly automated and basically simple, most unmanned or intermittently manned, remotely controlled, operate from CRPC, CPLC controlled by laser communication link via relays. Material transportation to Cynthia from FS, say, 120 miles away by electric cars via high-speed electromagnetic trains, and distant FS can burn cargo ballistically to receiver fighters. 2 minutes, okay. Ballistic system for cargo transport, centrifugal launcher with curved launch tubes running on magnetic cushions propelled by electromagnetic bilinear motors.
Energy will be provided by fusion power plants, initial build-up of a solar reflector swarm, Solecta will hit the site 120,000 square kilometers, dominating a 200,000 kilometer area. Biospheric Novaterra and technospheric sinks have become the pillars of, on which tropospheric Selenopolis and lunar civilization rest. Last stage, the Selenopolis and the Selenosphere, a fully developed lunar world with a large population underwritten by industry. Upon a strong economic foundation, a very high degree of self-sufficiency, food production, and a powerful fusion energy base. Progressively moving from massive imports from Earth to economic growth, population increase, a degree of financing by lunar capital. Evolution of social, economic, and cultural extraterrestrialization brings to an economical, political development. The aspire is stating which trade relations with Earth are based on raw commercial equality. This means mutually complementary value generation, where lunar civilization is not in a receiver position vis-à-vis Earth. The resulting high level of fiscal and economic self-determination and attraction of terrestrial investment capital encourages political implementation. Will it be a colony of Earth, part of the common heritage of terrestrial mankind, or will it be an independent political entity with Selenians in control of their own world? Okay, have to go quickly to the end. The presentation will all of the presentation will be available on our website, so it can be consulted even after this conference. Okay, I'm showing a few pictures from the paper Carterike, a low agricultural zone in Selenopolis. Okay, resort areas, okay, many things in Selenopolis, Selenosphere, comfortable vehicles with development of lunar habitation, which is a key milestone, a new environmental niche. Okay, the overall complex would eventually house many 100 million people. Christmas in Selenopolis, this is a famous picture. And okay, fusion, nuclear fusion energy. Okay, Kraft-Erike was definitely in favor of developing nuclear fusion energy on the moon because of the abundance of helium-3 that is required for fusion. And helium-3 could also, of course, be delivered as a product to Earth. Fusion energy for Earth, byproducts and outcomes of lunar fusion energy, many things also in this. And okay, resource extraction and processing, and lunar transportation systems. Okay, just to show you what is in this paper. It's very interesting and worth to be read and studied. And of course, we can think that the lesson by Carterike is a methodological one. He thinks in terms of a strategy. And I think strategy is a key word for space settlement, as we already said and commented in the past day. Okay? So.
Okay, thank you very much. Thank you, Adriano. Very comprehensive. So quite, yes,
Change the camera again.
And of course, in Erike habitat, we will have also a library where, yeah. Okay, when you are flying there, then you should bring that along. Excellent. Okay. Good. Any question? One short question for Adriano? There were many, so much material, but okay, that's clearly important work to follow and to see also how we can also adapt some of the new technologies to this, visionary ideas. Okay. Yes, I have. Okay, so Jacob, you have a point. You raise your hand, so I give you the floor. Oh, okay, I thought.
Yeah.
Yeah, okay.
Very good. Just a question. Adriano said we'll share the presentation. Very enthusiastic.
Oh,
Something happened to the audio.
yeah, to the audio. You mute yourself, but maybe you are looking. Okay, there will be an article also linked with this presentation, Adriano. Yeah, that's a question.
Yeah, we will have an article.
Yeah.
Yeah.
So, okay, clearly an article can be shared about that, that summarizes the main point and also some of the visuals.
Yeah.
Okay, so let's move, because of time, to the next talk. And that's by James Burke, so the Executive Director of Mars Society, and about Mars settlements in virtual reality. Jim?
Yes.
Excellent.
Hello, everyone. I'm coming to you from the US. It's very early morning here in Seattle. Let me go ahead and share my screen. I'm going to just play a video of our VR application as it's currently working. And I'll just kind of talk over that. So give me one moment here to set this up. All right. You guys see that okay?
The video is amazing. Your audio is a bit saturated. So if you make a bit of effort also to articulate for some of our non-native.
Yeah.
But
No worries. Is this better, Bernard? The audio better now?
Maybe we can.
I can hear you well, James, and the video looks great.
Okay, excellent. So maybe we
awesome. So, all right. So I'm just going to press on. So Mars Society, we essentially have spent the last 4 years on this project. We did a crowdfunding campaign in 2018, and our goal was to raise $25,000 for this project that we can make a digital twin of our station in Utah, the Mars Desert Research Station in the Utah Desert in the United States. So we started this campaign and we actually exceeded our goal. We raised $31,000. We took that money in 2018, summer of 2018. We hired some folks to fly a drone and scan a square kilometer of terrain around our station, as well as do some advanced techniques to capture the buildings. So a technique called photogrammetry, where you take the high resolution images and overlay it on points in space and that gives you a 3D object that's based on a real thing. We showed this application at a bunch of different events in 2018 and 19 and 2020. But we wanted to do more. We wanted to really build this out as a great crew training tool, as well as a more higher resolution public outreach tool. And we wanted to update the technology so that it could be used on modern headsets like the Oculus Quest 2 is the top of the line one right now. And so we did another crowdfunding campaign in 2021, and this time we raised over $100,000. And so all last year we were hard at work with our team, Mixed Reality in Seattle, Washington. Those are our partners on the project. And they've built over, they're one of the greatest VR companies in the industry. They've built over 100 applications for different, like Boeing and Microsoft and others. They built a version of the Space Needle here in Seattle in VR that you can check out. But so we partnered up with them, and they put a lot of time into it last year. And so now we actually have a fully usable campus with objects in it. So right now the video is showing someone going into some of the buildings. They can actually pick up objects. We actually have a demo of, so here's here's our one of the buildings in the facility. There's some objects you can pick up. I'm going to actually play a different video that has the suit donning and doffing procedure, which is really important for the folks that are out in Utah to learn how to do. So that was one training procedure we wanted to make sure we had in here. Let's play that. So here's the person's inside the main habitat, and there's all the different helmets and backpacks. And so if you're staying at the Mars Desert Research Station, one of the things you have to do before you go outside, if you're in a simulation, is put on your helmet and backpack. And so by having this available in VR, we can get people used to where in the facility this is and what the exact procedures are, and they can practice it at home so that when they actually get out to Utah and are on a crew and in simulation, they know where everything is, and it's just second nature at that point. So so we're pretty happy with this project, and we want to do more with virtual reality, but so far this has been a really good tool for us for public outreach. We've showed it at a lot of events in the United States, different space, like the Yuri's Night event here in Seattle. We showed it to about 200 people at that event. And it was a great experience for someone that doesn't really know much about space. They can just put on a VR headset and walk around on Mars. It looks just like Mars, even though it's Utah. And so now we're essentially working on a field science demo where we could have someone that's actually out in the field in Utah in a simulated suit, on a crew, and they could actually have a real-time communications link with someone back in the habitat with VR, with the VR headset on. And that way that the person in the VR environment could actually help the person in real life explore and coordinate sort of a campaign of field science. And so this is a concept we want to really demonstrate and get good at, and have some new tools that will allow us to do it well, not only in MDRS, but other demonstrations we can do outside of that. And so that's kind of the area of growth for this VR project, is showing how to do real field science with a telepresence helping you along when you're in the field. So the way we're going to do some of that is we're actually going to use amateur radio spectrum to transmit data between someone out in the field and the VR app, so that someone in the VR app can actually see a representation of the person in the field, and vice versa. Maybe the person in the field could have AR goggles and have a representation of the VR person. So we really want to kind of enable that real-time communication and collaboration between the two. And so that's kind of what we've been working on with the VR project. There's a lot more we can do. There's a lot of, I mentioned in my talk yesterday here, there's a lot of 3D models of different Mars habitats that people have designed. We had a contest a few years back at the Mars Society to get a bunch of Mars colony designs generated. And a lot of the work that was done, even though that people were turning in a paper, they also made 3D models in some cases. And so it's not that hard to take an existing 3D model and put it into VR. And so we could have a full-size Mars base that you could walk around in. It's just a concept. But this could be a really great tool to tell the story of different settlement designs, and also actually try them out, actually see how they work as a real facility in VR. So that's kind of a couple areas we want to go in the future. It'd be great to use VR for events like this. We had our virtual conference last year, and we had a VR room there where people could log in on a VR headset and watch our conference on a big screen in the VR room, where you could actually ask a question in VR, and it was the VR room showed up as an attendee on the Zoom call. So we actually had someone asking a question to one of the live speakers, like the deputy administrator of NASA was one of the speakers that we did this with. And it was real slick experience on both ends to not only see the VR room as a Zoom attendee, so you kind of see people, cartoon-like versions of real people asking questions and walking around in the room. But then also, if you're in VR, you're actually able to watch the Zoom call on a big screen, talk to people that are there, you know, make new friends and network with people. So that was a really cool concept. We use a technology for that event called AltSpace VR. But I could imagine a situation where we have our own sort of year-round VR event happening where people can just log in and talk to each other about Mars and walk around in different base designs, walk around in our campus in Utah as a digital twin of that. You know, that's kind of, I think, the future. You can almost think of it like a Mars metaverse, right? So that's an area I think we'd like to work in as well. And if you guys would like to partner up with us on that and help us make that vision a reality, we'd love to work with you. So with that, I'll take any questions there are.
Okay, thank you. Thank you, James. Yeah, are there some questions from the yes, Sabine?
Hi, James.
Hey, Sabina.
Hi. I have a question. The Mars rover is taking frequently pictures, and is it planned that you have a real Mars surface in your virtual reality program?
Yeah, actually, we worked on that a little bit. We took a slice of a high-rise image from the Mars Reconnaissance Orbiter mission, and we turned that into a terrain that you could actually walk around. And it's so big, it would take too long to walk around, so we made the Mars helicopter work in there, and you can actually fly around in the terrain or drive a rover. And that's actually something we'd like to have as a museum exhibit. You can imagine going to a museum and you can like sit in a small chair that gimbals and have a VR headset on and fly the helicopter or drive a rover. We actually have that working now in the lab here. And so yeah, we have a prototype, I'd call it, Mars terrain based on a real high-rise slice. But we could certainly do more. I mean, there's a lot of opportunities, I think, to take NASA data and turn it into VR terrain. It's not a well-designed process. Like, it hasn't been done a lot by people, but it is an area we have done the one terrain with, and then we'd like to do more. So you can imagine like having a future application where you'd have the full globe of Mars and you could just zoom in anywhere and then start walking around there. That would be a great visualization tool. And there's coverage of the whole planet from Mars Global Altimeter data. And then you can overlay higher resolution terrains as you had them available from high rise. So all the pieces are there to do an application like that. Someone just needs to go do the work. So.
Because I see at the moment it's still like the fan factor, it's more visible, but I think if you have a really Mars surface, then it is developed further. Maybe they can use it for a real training, astronaut training program on a surface of Mars, and you can see what, yeah, you know?
Yeah.
And maybe you can do it for the moon too. I know you are all in the Moon Society, so.
Moon, Mars together. Earth, Moon, Mars. This is what I've learned from Buzz Aldrin, actually. That's his motto. Yeah, so thank you very much. Oh, no. There is Jeremy raised his hand. Yeah.
Hi, James. Dust mitigation is going to be a major aspect of Mars EVAs and on the moon as well. Do your VR simulations include that kind of activity?
Include mitigation?
Yeah. No, look, like brushing down your EVA suits are when you come back inside?
Right. We don't currently, because that's not really part of the MDRS simulation. So we're trying to kind of make a digital model of what we do at MDRS in terms of the procedures and the hardware. But it is true that dust is going to be an issue with EVA suits on Mars. And I think one of the ways that that will be addressed is you may have a design where the suit's always outside, and
yes,
you just dock the suit to the building and go inside through the back, so that you're not bringing the whole suit inside anywhere. That's probably, I think, what people will do on Mars, something like that, or maybe a situation where you walk into one sort of airlock, get out of the suit, and then walk through another lock so that the suit is still kind of separated out from the habitat, and there's and whatnot. Those are, I think, concepts that probably will be how they do it. But no, we haven't put that into the VR app.
I actually suggested some years ago that Mars missions might have a major sponsor being Hoover or Dyson.
Yeah.
Yeah, maybe.
Yeah. Okay, well, let's see. Nice idea, but you have to follow it up to execution. So talk to the official. Yeah, thank you very much, James. Bravo.
Thank you.
So, if the speaker from this morning can stay, because before we go to this very interesting solar physics visit and demo at 12:30, so that's in about half an hour, we would like to have like a 10 minutes wrap up with all the panelists. But before that, we'll have the last talk from the session. And this is about habitat in the cis-lunar city. And that's given by Gennaro Russo, who is the director of the Center for Near Space of the Italian Institute for the Future. So, Gennaro?
Yeah, thank you very much. Thank you for the invitation to give this presentation. I try to share my screen. Tell me if everything is okay, as I hope.
Yes, this is a presentation.
Okay, good.
Thank you, all clear.
Okay, so just a couple of words about the Italian Institute for the Future. This is an association dedicated to the anticipation studies in all kind of sectors. And the Center for Near Space is the center of competence of the Italian Institute for the Future dedicated to space. Center for Near Space because we are thinking near in a different kind of sense, let's say. We are thinking of the development of humanity into space. So not we do not like talking about colonization. We talk about expansion of humanity in space. So in particular, so we emphasize very much the distribution, dissemination of the space culture. We think strongly about what we call civil astronautics. Then, as we know very much on Earth about civil aeronautics, and then private user community for what concerns space. We develop concept studies trying to understand on the basis of the signal of today what will be the concrete and realistic world of tomorrow. And we, in order to do that, we set up interdisciplinary and intergenerational, let's say, groups and debates involving many kind of people, different kind of competences and simply sensitivities. So, and everything is based on one very, very fundamental point. Expansion of humankind into space has already begun. There is no doubt about that anymore. So, in particular, talking about the habitats, we say that that wonderful piece of engineering that is the International Space Station is today clearly a sort of Paleolithic design. It's an old kind of design. Very nice, very good, very well, but it is absolutely similar to the very first cars of centuries ago, and that's the reason why we are trying to investigate, to imagine what will be, realistically speaking, the configuration and the habitats of tomorrow. So we have set up what we call Orbitecture. That is a working group. It's a contraction of orbital architecture, and not dealing only with orbital things, but it's a generically used for all kind of space habitats. And the major criteria that we have identified is to minimize weight per capita, maximize space per capita, integration different activities that are today inconceivable in an ambient like the ISS or similar, or even the gateway, the moon gateway. Because simply these kind of habitats are still today built for very selected kind of people. So we are, vice versa, we are thinking about, in brackets, ordinary people. And about that, first of all, let me say that we have tried to identify what will be the future. You see 2069, that is, symbolically speaking, 100 years after the very first step of the man outside the Earth. So it's a symbolical date, and we do expect, we do believe that according to the signal of today, there is a possibility, a concrete possibility that by that date we will have a 1,000 inhabitant, let's say, cislunar city between the Earth and the Moon. We think that we will have something like a dozen districts dedicated to different kind of activities, as we will see shortly. The macro functions remains very simple, but first of all comes industry, and there is a specific reason for that. There is no possibility that governmental money will fund such kind of development. No government money will be enough to do that. So it is paramount, it is paramount that it's a business-based activities be incentivized and be, let's say, realized. So industry comes first, research is fundamental, of course, then management of all the districts, that is not at all an easy task, and of course also resorts, including simply habitats for the workers, but only for tourists, etc. I will, of course, I will fly over all the concept. This is an indication of the population, distribution of population, these 12 kind of, districts. You can see that there are a number of old nodes that are fully devoted to hotel, that means for tourism if you want, other for industrial processing. Of course, we are talking about main functions. All these kind of districts will be anyway dedicated also to secondary activities. I don't want to go through, but just to give an indication that over 1,000 people, let's say that one third will be dedicated to management. And apparently, in the sort of, how to say, only a relatively small number of people will be dedicated to research. And this is because research is publicly funded at the end, or partly at least. And what is very much important, that industry is the core, the pulsing core of this cislunar city. Well, we have cited the number of these districts. I will present only a few things. This is the Space Hub. This is a node, a node that is supposed to be located in the Lagrangian point L1. It's a sort of, the dimension is 100 people district. I must underline that we did not define the form, the shape of this district a priori. We just tried to identify the functions, the needs, engineering needs, operational needs, and then people needs in general. And summing up all the things, we arrived at this kind of configuration that, logically speaking, is a planetomorphic configuration. So the philosophy is a planetomorphic configuration. I underline this because you will see something else shortly. I don't go into many things. You can see anyway that there is a pressurized volume per capita that is something like 5 times higher than the present International Space Station, and things like that. Realization, the central bubble, central sphere is a 50,000 cubic meter sphere. Is based on, will be realized by an inflatable structure. Once inflated, there will be a chemical reaction because of the internal gases and because of the sunrise rays, etc., that will let's say change the configuration of the matter, and then we will have a rigid sphere. The other toroids will be realized by additive manufacturing in space by a toroid construction machine that we have conceptualized some years ago. And then spider fab systems will be very much used for realizing. We have estimated that the realization of such kind of nodes will last something like 3 to 4 years. And keep in mind that the diameter of the big toroid is 200 meter, roughly. Here are some elements for what concern, the distribution of the capabilities and activities. Microgravity laboratory just near the rotation axis, then reducible gravity labs, and then we will have lunar and Martian labs. The rotation of the system and the dimension of the toroids are tuned in order to get the lunar simulate the lunar gravity on the inner toroid and the Martian gravity in the outer toroid. This is a toroid, and again, the section of the toroid. The major elements are the following. We will have a 3D printed structure, transparent, mostly transparent structure of cover anyway, and we will have 2 kinds of accommodation: a single accommodation for essentially workers, and double accommodation for double room, let's say, for tourists. Because it is an indication. You will have two corridors running around the toroid, and then there is also the space for all the services for the toroids. Keep in mind, this is a corridor typical of toroid. Keep in mind that 2/3 of the entire volume of the entire station will be dedicated to cultures, to green, in order to produce oxygen and foods for the inhabitants. This is a typical double bed accommodation. There are also other kind of elements. You can see this kind of accommodation are distributed around the toroids, and the green toroid is fully green, fully dedicated to culture, foods and oxygen production. Condensation areas are very much important. 100 people is not a big number, but it is important to create, common sense, commonalities, and civil society. This is another view of a part of the toroid. Now, the second example I want to show you is district on the moon that is absolutely dedicated to industry. So this is a geodetic construction. The approach in this case, is fully different from the planetomorphic, let's say, logic. You see here it is underlined that we use what we call archaeological approach. Exactly as with the archaeologists do on Earth, in order to minimize the impact with the ground, we use this kind of suspended configuration. Only few points touching the ground, and everything else is suspended. This will give us the opportunity to construct this kind of building, let's say, in a shorter time, not needing to move big masses on the ground, not needing to destroy, let me say, in a way, the ground of the moon and things like that. This is a 50-meter diameter hemisphere. I will not go too much through. The idea is to minimize, as I said, the contact with the ground, realize, first of all, the geodetic cupola, and then start from the highest level of the building in order to create immediately the trees and the production of oxygen and food, etc. And then we will move downward, creating the second, third, and fourth floor for laboratories, industrial activities, and things like that. And this is just a possible, let's say, development. More than one cupola, we can have also 2, 3, or 4 cupolas together in a modular approach. I will just say a few seconds about this video. I hope you can see it. It is a bit slow, but I will not say the entire duration, but just few seconds more. 120 people on the lunar fab, dedicated to industry, dedicated to extracting material from the moon surface, and making a number of production processes, not all, of course, in order to let's say, arrange materials and subcomponents and then distribute. I'm not said yet that the 12 districts will be connected each other by a system of transportation, and every district will have 2 arrivals and 2 departures per day, per terrestrial day. So this is not much, but it is quite a number, as we will see shortly. What is that? Something. I'm sorry for that. Okay, seasonal transportation. This is the system that we have estimated, talking about the sort of underground, metropolitan, not underground, metropolitan. We will have a couple of Lagrangian, couple of circle lines, what is called Earth-Moon circle line and the Lagrangian circle line, and then we will have more, in brackets, local lines. This is, of course, symbolically again, but what is interesting is that we have estimated the number of the dimension of such kind of transportation, 120,000 passes per year, and 100,000 tons cargo per year. And this is done by not big heavy launch and heavy transportation, but relatively small systems for 10 passengers and 10 tons each. All seem equal, apart from some changes for what concerns the departure from Earth. And we will have 22 operational transportation vehicles plus 5 vehicles in maintenance shift. This will guarantee a full set of scheduled flight in 1.5 terrestrial days, and so and all kind of numbers are coherent with each other in terms of dimension of the districts, in terms of mass of material to be distributed, in terms of production material, for example, on moon surface, and with the cost elements that you will see in a moment. Space economics, you can see here the annual budget. There is no time to enter into detail, but we have identified major elements. And you can see that the cost for the annual budget, don't forget, this is just annual budget in the year 2070. The major cost is infrastructures, much higher than all the others. And revenue must be from industry. Industry for changing and developing the products or semi-products from space, let's say, elements for space utilization, but also for Earth utilization. And here you can see the cumulative economic flow from now, essentially up to 2070. And you can see that we estimate a global space economy on for the lunar city, including part for Earth, of course, of 60 trillions or giga euro, if you want. Of course, there is no time to enter these elements, but we believe that this number are, let's say, balanced at least with respect to the elements that we have identified. Just this is the last statement, the last picture that Adriano knows very well, because we together developed such kind of graph years ago. And in one word, we can say we have to say that, and we have to admit and recognize that the age of space industry has already begun, and is certainly one of the major economical cycle of mankind. I think I can stop here.
Thank you.
Thank you so much.
Thank you very much, Gennaro.
Okay.
Do you have some question before we go to the panel? Yeah? You want to come here?
Yes, it was a very excellent presentation, but I have just one question because of the shelter for the lunar habitats, because of solar flares and of micrometeorites and of cosmic rays. I think this would require an answer.
Okay. Yeah.
I'm sorry, I understood that the question is related to the lunar, let's say, cupola or lunar fab, but unfortunately I've not heard very well because there is an echo. Can you repeat the question, please?
Okay, once more. I missed a shelter by lunar material, especially by regolith, to cover the station you have designed for the lunar surface against meteorites, micrometeorites, and solar flares, and of course rays.
Galactic cosmic rays.
Cosmos.
Yeah, of course, again, we say, I repeat, we try to project into the future the so the technological capability and knowledge of today. First of all, I must say, I'm not mentioning at all, but both for both the two examples I made, there is a huge use of water around all the ambient to mitigate the radiation. Of course, it's just a matter of mitigation, and we will not solve 100% the problem. And this is one issue. Then there are kind of materials that already know today that has some capabilities in doing that. And there is also, we do not use the lunar regolith. We do believe that combining the actual capability of certain material, we're combining with the development of materials in 50 years from now, and water, maybe something into the water, also mixed into the water, will altogether create the condition to let's say, satisfactorily solve the problem. This is our anticipation. I will need more time to enter more details. Maybe there's no time. Eventually, I can share certainly documents for presentation, publication in that sense. I would be very much, glad to do that. But for what concerns the activities, the industrial activities on the moon, even the transportation, even the local transportation system will be the surface transportation. I mean, will have exactly the same kind of protection: water plus certain kind of materials. That and also some prospective, capabilities, characteristics of materials to be developed from now to that time.
Okay, thank you very much. So we just have a few minutes now to have a kind of a wrap up for this session. And So Jerry, let's include you in this wrap up. And I think the wrap-up should talk about what we are going to do next. And actually, I was very interested by the different concepts that were proposed. Some of them look quite long in the future, and we have some analog habitat that exists now on Earth. So one question is, what could we do in between to implement the first step? Another thing as well is, actually, I was invited this year there was a class of space architecture given at the International Space University in Strasbourg, and they worked by groups on different concepts. There were concepts of orbital habitat, actually with a pure circle as 1G, and I proposed them, why don't you put something in between to learn lunar G, Mars G, and I saw that this idea was already explored by you, but they worked on Mars habitat, Moon habitat. So could we eventually, as a follow-up, inspire some of this school of space engineers, scientists, architects, and make them work also on some of the concepts that you have proposed? So that's a question to you. Do you see that that's something that we could, as a result of this Space Renaissance festival, get a challenge that we could give to the young professional studying space? Anybody would be up to help us to challenge this young professional? So any of you has a comment on that? To work on your concept and yes, have also independent view by young professional to analyze them? Who wants? Somebody raised a hand, or Werner? So as you are here, so do you see that in your committee we could involve some of these young space architects? And then I give the floor.
Yes, I think we have today seen a lot of proposals for space stations, as well as on the moon, as well as rotating space stations in Earth orbit and somewhere else, and also on Mars. Maybe we could combine our efforts, but we must establish some kind of a system, of a systematic way to work together.
Yeah. Excellent. So we had Jerry that had raised his hand, and then Jacob.
Hi. Werner mentioned the Island Zero proposal in the presentation earlier. And the reason that we came up with this idea as part of the space project, which was to look at how something like an Island One might be developed in modern times, because when it was originally put forward back in the 1970s, it was deliberately restricted to the technology available at the time. And that was so that nobody could say, well, it's a nice idea, but it depends on this and this and this that we haven't invented. And in the last 40 years, of course, technology has improved and advanced considerably. Our computing power is many orders of magnitude beyond what it was. And our robotics capability mean that instead of a construction force of 2,000 people, I'd be surprised if we need more than a couple of hundred, because we would have robotic production and 3D printing and all kinds of things. But before we get to that stage, we will need to build the facilities that are going to house the construction force. And before we do that, we'll need a smaller facility to build that larger one. It's a bootstrap process. And so having got Island 1, 2, and 3, we came up with this very small scale setup, which we called Island 0. But the point about it is that it would rotate to provide simulated gravity, which is so needed for people who are going to be in space for long periods of time. Another point about Island 0 is that we could choose the speed of rotation. So we could decide what simulated gravity we would have. And one of the first questions that I put to my project was, do we need 1G? Because that's always been assumed in all previous habitat designs. I said, I'm sure we could get away with 0.9G, perhaps 0.8, even 0.7.
We should do some medical research to see what.
Now that's the thing. See, so Island 0 would be able to.
We cut it short, Jerry. You had room for a question. Please end your statement. Then we have Jacob. And
that's okay. No, I'm just saying that Island 0 could produce that medical research.
Yes.
We could actually put people up there and find out human tolerance at different gravity levels. So there's a proposal then for short-term activity.
Yeah, tolerance and also learning about, the human physiology, even for us. Excellent. So we had Jacob that wanted to intervene, and then we'll have Adriano before we have the break. Jacob?
Yes, very small comment. I think this conference festival is great because it. I'll switch off my video. My internet connection is not that good. Is it better this way?
We hear you well. Yes.
Okay, very good. I think this conference festival is great because it links us. All great minds here should collaborate. So we should organize follow-up meetings. And the first step might be to create such a systematic way of collaboration as Werner suggested. And for this, and to create this sort of foundation for continuing our work. And perhaps even Asgardia can help in this. You never know, as a sort of a overarching country idea.
Mm-hmm. Okay, so clearly, yes, we have a good way to work together on practical projects, also some of the midterm one, and also involve some other part of the community, like the young professional, like the rest. So we take this as an action out of this festival. Adriano?
Okay. Yeah. We have some proposal for practical collaboration activities. First of all, I wanted to say something, very few words about Jerry question, do we need 1G? It depends from our requirements, let's say, because if we want to study the effects of lower than 1G gravitation, then we can experiment with 0.5, 0.6, 0.7, and so on. If we talk from an anthropological point of view, for the space settlers, the people that will be resident in space, I think 1G is needed, because even if they use habitat to live at, I don't know, 0.8, however, to come back to Earth would be painful for them after some years that you stay there. So, okay, just one point. Coming to the proposal, okay. We at the Space Renaissance Academy have created several committees. Some of them are already working, some of them are still on the paper, of course. However, we have two committees, one on artificial gravity and one on space habitats. So, what will we do with this committee? What will we try to do? We are also working together with the International Space University to conceive and manage workshops for their students. And we are thinking, we are giving some workshops that will require students to draft a statement of work for some project. For some projects that are for civilian space development. So like exactly the orbital facilities we are imagining. And so we will ask students to think about the requirements. So what are the scientific requirements, the user requirements, the human requirements, and so on. And to draft a statement of work for phase A feasibility study. I think that if some of us will join us in these committees, we could work together to generate new ideas for workshops to be submitted to students, and then maybe some of these works will go to either to NASA for proposals. That will be very attractive for students to work with us on these projects. So
okay, let's do that. Okay, let's do that. So I think we will entrust our current committee to include some of the speakers of today, and we will also work with some of the space universities, space architecture, and also then we can also provide mentorship, coaching, give directions, be as customers, and eventually then we go also to space stakeholders to get some of the next step. Okay, well, that's quite a practical way forward. So thanks to all the speakers of this morning for the questions, the debate, very interesting concept, our audience. But now we have to take a break. And of course, we have to be flexible. And if you look at here, the sun is not yet visible. It will be in 1 hour. So we are going to now take the lunch break immediately now, and we will reconvene at 1:30, because there is a chance we can see the sun itself, and then we will have the solar physics demo at 1:30 exactly. So let's go rush for lunch or for enjoying outside, and come back at 1:30 for the visit of the solar physics laboratory cabinet and possible real observation of the sun. So all the best to all of you, and the session on astronaut training and analog will start again at 2 o'clock Central Summer Time, which is noon GMT. Yeah. So see you all. Have a good lunch.
Thank you.
Have a good time in between. Thank you.
Nice to meet you guys.
Thank you. Thank you. Bye-bye.
Okay,
Let's
welcome.
keep in
Thank
touch.
you.
Yeah.
Keep in touch, John. Yes, and the other.
Okay.
Bernard, I must just say, it's so nice to see you and Adriana and Sabine and Werner all together, instead of all having to be on separate Zoom screens.
Yeah, yes. More and more we will be acquiting real presence. Yeah. All the best.